Let's say a company rolls out a new eco-friendly light bulb. On the box, they boast that it lasts over 10,000 hours. Or maybe an insurance company brags to investors that they've driven their claims processing costs down to under $60 per case. As consumers or investors, we need a way to verify these claims, separating actual reality from marketing hype. The core problem is that we can't test every single item a company produces. If we left millions of light bulbs on until they burned out, testing the entire population, we wouldn't have any product left to sell. Instead, we have to isolate a small sample, say 30 bulbs, and use that tiny group to make a judgment about the entire production line. But this introduces a massive risk. What if we just happen to pull a lucky batch? Our 30 bulbs might perform exceptionally well purely by chance, throwing off our entire conclusion. Guessing whether a sample is truly representative or just a statistical fluke is too unreliable. We need hypothesis testing, a rigid mathematical framework designed to calculate exactly what is a coincidence and what is the truth. Every hypothesis test begins by setting up a formal face-off between two opposing claims. On one side, we place the null hypothesis, written as H0. This is our baseline assumption. In the case of the light bulb, the null hypothesis assumes the company's claim is false, and the bulb is just average, lasting exactly 10,000 hours or less. On the other side sits the alternative hypothesis, or H1. This is the challenger claim we are actively investigating, the assertion that the bulb genuinely lasts more than 10,000 hours. To judge this face-off, we rely on test statistics. These are mathematical formulas that weigh our sample data, and the specific formula we choose depends entirely on what information we start with. This handwritten slide shows the z-test. We use this formula when we already know the historical variation, or standard deviation, of the entire population. It plots out exactly where our test results fall on a normal distribution curve. But often we don't have that historical data. This next slide shows the t-test, which relies solely on S, the standard deviation of our small sample. The t-test includes a degrees of freedom adjustment, making it more forgiving of limited datasets. Selecting the correct formula ensures our mathematical rigor accurately reflects the real-world limitations of our data. Let's return to our light bulb investigation. We test our sample of 30 bulbs, and the results come back. They only average 9,900 hours. The result is lower than the 10,000 claimed, but is this enough evidence to definitively call the company a liar? Or does a 100-hour difference fall within a normal margin of error? This is where we calculate the p-value, shown here as the shaded areas under these curves. The p-value is the exact probability of getting our 9,900-hour result if the company's claim were actually true. To interpret that probability, we set a strict threshold called alpha, our level of significance. This is usually set at 5%. Alpha draws a hard line between normal variation and highly suspicious data. This chart visualizes that threshold. The blue shaded section on the far left tail is the critical region. If our calculated test statistic falls into this zone, the data is so extreme that the original claim cannot hold up. The golden rule of hypothesis testing is simple. If the p-value is smaller than our alpha threshold, we reject the null hypothesis. You'll often hear statisticians say, if p is low, the null must go. By relying on p-values and critical regions, we strip away emotion and bias, leaving an objective, mathematical threshold to declare a corporate claim validated or dead. Because we rely entirely on a sample to make assumptions about millions of products, our math can never be 100% certain. We are dealing in probabilities, which means we can still make mistakes. The first mistake is a type 1 error, or a false positive. This happens when we reject a true claim and sound a false alarm. Imagine an assembly line filling boxes of candy. A type 1 error means our sample data tricks us into halting the multi-million-dollar production line because we think the boxes are underweight, even though the machines were running perfectly fine. The second mistake is a type 2 error, or a false negative. This occurs when we accept a false claim, letting a very real problem slip through our testing undetected. In the factory scenario, a type 2 error means we keep the machines running under the false assumption that everything is fine. We end up shipping thousands of genuinely underweight candy boxes and face massive customer lawsuits. The alpha level we set at 5% is actually a risk management dial. As a business moves the alpha slider, they actively choose whether they would rather risk a false positive factory shutdown or a false negative lawsuit. These rigid protocols function as a calculated risk management tool, empowering modern society to navigate uncertainty and separate corporate fiction from statistical fact.